Hello, nuclear energy, temperature of deuterium fusion reaction. The question is the temperature requirement for the DT fusion reaction. So we have to find the temperature. What it should be the temperature of deuterium and deuterium. So this is H12. This is deuterium. And Z is equal to 2 and R of D, radius of this one is 1.5 Fermi, and 1H3 is tritium. Z is equal to 3 and RT is equal to 1.7 FM Fermi. FM is equal to 1 10 to the power minus 15 meters. So when this is D and this is T, and they are moving close to each other with the kinetic energy Ke. So head-on collision. So this is then they collide each other. So this one, so this one, this and this, and this is a radius to center radius. Distance. So here the nuclear forces take play, come into action, and electrostatic repulsion is also there. So the kinetic energy of the both should be equal to the electrostatic potential energy. Of this system. So 2 kinetic energy double is equal to the constant 4 pi epsilon into E of first one, E of second one, divided by the distance, R1 plus this one, RD plus RT, which is equal to 3.2 Fermi, RD plus RT. And if you substitute the values, this is equal to 9.0 into 10 power 9 Newton meter square over Coulomb square into this one E square, 1.6 into 10 to the power minus 19 whole square into Coulomb square divided by RT. RT is this one, 3.2 into 10 to the power minus 15 meter, into converting it into million electron volt, 1.6 1.6 into 10 to the power minus 19 joule over electron volt, 13 million electron volt. So this will be equal to 2 kinetic energy, which is equal to 0.45 million electron volts. That means the kinetic energy is equal to 2 Ke. Kinetic energy of the single particle should be equal to 0.22 million electron volt. So this is this one. So that is the one condition. And from here, kinetic energy to uh, temperature, we will use the uh, kinetic theory of gases. So this one, it is that the kinetic energy is equal to average kinetic energy. This is average is equal to 3 into 1 over 2 kT. K is a Boltzmann constant, and T is the temperature in Kelvin. In Kelvin. So from here, the T is equal to 2 by 3 Ke over Boltzmann constant. So this is equal to 2 by 3 into kinetic energy is 0.22 million electron volt divided by 1.38 10 to the power minus 23 Boltzmann constant joule per Kelvin and multiplied by so this is in million electron volt. So this will be multiplied by a factor 1.6 into 10 to the power minus 13 joule per million electron volt. So this one, and this will give us the temperature which is equal to 2.0 into 10 to the power 9 Kelvin. So this is the temperature required for the fusion, and the kinetic energy of the two molecules, each one should have a zero point 0.2 million electron volt, and the temperature in this condition is very high, of the billions of or billion Kelvin. Because it's an average, so it should be less than, so in between 2 to 4 uh, into 10 to the power 8 Kelvin is the required. So zero point 0.2 to zero point 0.4 billion billion of Kelvin. So this is the requirement of the fusion reaction.